Picture this. You have two tiny particles. They're created together, and then you send them flying apart, maybe even to opposite ends of the galaxy. Now here's the weird part. The moment you measure something about one particle, its partner instantly, and I mean faster than light, knows and reflects that change. It's a connection that just seems impossible. So what in the world is going on here? Let's get into it.
You know, this idea wasn't just weird to us. It was so out there, so deeply counterintuitive, that it really bothered one of the smartest people who ever lived. Albert Einstein famously called it spooky action at a distance. He was convinced that it couldn't be right, that it pointed to a huge flaw in the new mind-bending theory of quantum mechanics.
So what is this spooky action? How does it actually work? And here's the big one. If Einstein was wrong about this, what does that tell us about the very nature of reality itself? That's what we're going to unpack. We're going to see how quantum entanglement went from being this weird philosophical headache to something that's literally building our future.
All right, first things first. To really get a handle on this, we've got to understand why entanglement is just so different from the world we see around us every single day.
And this really gets right to the core of it. Look, in our normal, everyday world, what physicists call the classical world, things are separate. You know, if I push a book on one side of the room, a book on the other side doesn't just magically move. They're independent. But in the quantum world, it's a totally different ballgame. Entangled particles don't act like two separate objects. They behave as a single unified system. They're connected, no matter how much distance you put between them.
So this shared identity, it has a name. It's called a quantum state, and it's all described by this one mathematical thing called a wave function. The easiest way to think about it is like this. It's a single set of rules for the whole system. It's not one particle telling the other what to do. Nope, they aren't sending secret messages back and forth. They're just following the same script because they're part of the same story. They're acting as one.
So how do they get this way? Well, it usually happens right at their birth. When particles are created together from a single event, say one particle splits into two, they can become entangled. They come into existence linked, with properties that are perfectly opposite. A good example is a property called spin. You can just think of it like a tiny spinning top. If you measure one particle and find its spin is up, you know without a shadow of a doubt that its partner, wherever it is, has a spin that's down. Their destinies are locked together from moment one.
And that idea, that connection across vast distances, that's exactly what drove Einstein crazy. It's what he couldn't get on board with, and it kicked off one of the greatest debates in the history of science.
So, back in 1935, he got together with two colleagues, Podolsky and Rosen, and they wrote this bombshell of a paper. It laid out what we now call the EPR paradox. And their whole point was to use entanglement to show that quantum mechanics as a theory must have some big holes in it, that it just couldn't be the full picture. Okay, so what was his problem, really? What was the one fundamental rule of the universe that he was so sure entanglement was violating? It all boils down to one core idea, the principle of locality. And that's a really basic concept in physics. It just means that what happens here should only affect what's right here. And, crucially, that nothing can travel faster than the speed of light. So Einstein argued, look, for one particle to instantly know what happened to its twin galaxies away, some kind of message has to be breaking the universal speed limit. He figured there had to be another explanation. He called them hidden variables, some secret information that the particles carried with them all along, pre-programming their results. And for a long time, that's all it was, a huge philosophical argument. Was it Einstein's hidden information or the pure weirdness of quantum mechanics? It seemed like we'd never know. But then, a physicist figured out a way to actually put it to the test.
His name was John Bell, and in 1964 he did something absolutely brilliant. He came up with a mathematical test, now called Bell's theorem, that could finally settle this thing. It was like drawing a line in the sand. If Einstein was right about hidden variables, the experimental results would be below a certain value. But if quantum mechanics was right, the results would be above that value. It was simple, elegant, and you could actually go out and test it in a lab.
And as you can see here, this is how it all went down. Starting in the 70s and 80s, physicists all over the world started running the experiments. And the results? They were just stunning. Every single time, the experiments violated Bell's inequality. They came out squarely on the side of quantum mechanics. The verdict was in, and it was unanimous. Einstein was wrong. There were no hidden variables. The universe really is just that spooky. All right, but wait a minute. If this connection is instant, does that mean we can build a faster-than-light telephone? Can we break the cosmic speed limit? This is probably the #1 question people have, so let's tackle it head-on.
The answer in no uncertain terms is no. You absolutely cannot use entanglement to send messages faster than light. Einstein's theory of relativity is safe, so why not?
Let's just walk through what happens. You've got your two entangled particles, far apart. An observer, let's call her Alice, measures her particle. The moment she does, that shared quantum state, the wave function, it collapses. Now, this doesn't send a message to the other particle. It simply reveals the state of the entire system. Think of it like a pair of gloves. You put them in two separate boxes and mail them to opposite ends of the earth. When Alice opens her box and sees she has the left glove, she instantly knows that her friend Bob has the right glove. No information traveled faster than the mail. The information was already there, hidden in the correlation.
And here's the absolute key, the kicker. The results of quantum measurements are completely random. Alice can't decide to make her particle spin up so she can send a 1 in Morse code. She just measures it and gets whatever she gets, a 50-50 chance of up or down. And since you can't control the outcome on your end, you can't use it to send any kind of meaningful message. So, no message means no communication. The laws of physics are safe.
Okay, so this isn't just a weird curiosity for physicists to argue about anymore. What started as Einstein's spooky puzzle is now the driving force behind a whole new technological revolution.
I mean, just look at this stuff. This is real-world application. We're talking about quantum cryptography, which uses entanglement to create communication that's basically unhackable. Why? Because if anyone tries to listen in, they break the entanglement, and you know immediately. We're talking about quantum computers that use entangled qubits to perform calculations that would take a normal supercomputer billions of years. This spooky action is being turned into real, world-changing technology.
Now it's pretty funny, actually. While every physicist agrees the math works, it predicts things with perfect accuracy, they still argue about what it all means. You've got different camps like the Copenhagen interpretation or the many worlds idea, all trying to explain the why behind it all. But for now, the what is clear. Reality is weird.
So when you boil it all down, what has entanglement really taught us? It's shown us that our common sense view of the world, a bunch of separate things scattered around, is just plain wrong at the deepest level. The universe, it seems, is far, far more connected than we ever could have imagined.
And that leaves us with one final, pretty mind-bending question to chew on. We spend our lives seeing a universe of separation, of you and me, here and there. But what if entanglement is pointing to a deeper truth? What if the most fundamental thing about our reality isn't the distance that separates things, but the incredible invisible connections that bind them all together?